In this video, we're going to prove that the cosine function is continuous for all real numbers. Now we need a few previous results before we can start the proof. First, we need to recall the definition of continuity at a point. And the way that was defined is that we said f of x is continuous at x equals a if the limit as x goes to a of f of x is equal to f of a. Next, we need to use a couple important limits of sine and cosine that were actually derived by way of a geometric construction on the unit circle. And neither one of these is a surprise. So first we proved that the limit as x goes to 0 of sine of x is equal to 0. And then we proved that the limit of cosine x as x goes to 0 is 1. And I'll post a link at the top to that video as well. So now we want to prove this fact that the cosine function is continuous for all real numbers. So what we're trying to do is take the limit of this function, the limit of the cosine function as x goes to a for any real number a, and we want to show that that's equal to cosine of a, and that'll complete the proof. And I suppose we should start by indicating here that a is just some arbitrary real numbers. So we're going to say let a belong to the set of real numbers. Now we set up the limit that we're trying to evaluate for the definition of continuity. So the limit as x goes to a of cosine of x, and we want to create a long chain of equalities here, and at the very end we should find out this is equal to cosine of a, and then we've completed the proof. And here's the clever trick for this kind of proof. I can say the limit as x goes to a, and then instead of writing cosine x, I'm going to write the cosine of x minus a plus a. So hopefully you agree that that's fair. I can subtract and then add back in the same thing without changing what's in those parentheses. But the point is that I want to exploit our formula for the cosine of a sum of two angles. And I'll be able to split this up into sines and cosines of x minus a. So we're treating that as one angle and then a. And note, just as kind of a preview here, that clearly as x goes to a, x minus a is going to approach 0. So that'll be useful when we get toward the end. So first we have to apply our cosine of a sum of two angles formula. So remember, the cosine of a sum of two angles is the cosine of the first, cosine of the second, minus sine of the first, sine of the second. So now we're going to use our limit law that says a limit of a linear combination is the linear combination of the limits. And I'll post a link up at the top to the video where we first discussed limit laws. Now keep in mind the cosine of a and the sine of a are both constants. So when we apply this limit law, we obtain the cosine of a times the limit as x goes to a cosine x minus a. And in our second term, we have a minus sine a, remembering that that's a constant, times the limit as x goes to a of sine of x minus a. Now at this point, some books are going to use the composite function theorem here, but the approach we're taking, because we've previously proven these two limits, the approach we're taking could arguably be done without any more in-between steps. I can see that the limit as x goes to a of the cosine of x minus a is going to make it so the argument of the cosine function is approaching 0. In other words, this is functionally a limit of cosine x as x goes to 0. If you want to throw in an extra step here just to be super careful, you could say let u equal x minus a. And then as x goes to a, u goes to 0. And I have the limit as u goes to 0 of cosine u, which allows me to perfectly match this prior result. Now we're always walking a tightrope in a semi-formal space in Calculus 1, and I think this is clear enough to not show that explicit substitution, but I thought you might want to be aware that you could do it that way. So as x gets close to a, x minus a clearly gets close to 0. This is functionally a limit as the argument of the cosine approaches 0, and we've proven previously that that's equal to 1. So this first term is going to reduce to cosine a. In our second term, we have a similar thing happening. We have a limit as x goes to a of sine x minus a. Now clearly, x minus a is approaching 0 in this limit, so it's the same sort of issue. That limit is going to give me this limit over here. The argument of the sine function is approaching 0. We've already shown that that's equal to 0. Now because that limit goes to 0, and 0 times anything is 0, we're done simplifying this thing, and it simplifies to cosine of a. That's exactly what we were trying to prove. The limit as x goes to a of cosine of x is equal to the cosine of a. So the cosine function satisfies the definition of continuity for any real number. And now we can celebrate our success by writing QED, that which was to be demonstrated, and we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the x-a+a logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.